Welcome back to New Findings of the Universe. Today, we are going to explore one of the strangest headlines you'll hear in astronomy. The James Webb Space Telescope has identified 6 potential rogue planets in the young NGC 1333 nebula, one of them so light it may be the lowest mass free-floating object ever found with its own dusty disk. We'll unpack what rogue planet actually means, how Webb found these objects, why one of them wearing a tiny disk is a big deal, and what the discovery tells us about how stars and planets form. Along the way, we'll connect this result to a larger story: stars that unmake planets as they age, and the cosmic fingerprints those endings leave behind. Let's start with the idea of a planet with no star. In everyday language, planet implies a world going around a sun. In research, we use a more technical yardstick: mass and context. Anything below the deuterium burning limit about 13 times the mass of Jupiter counts as planetary mass. If it isn't gravitationally bound to a star, we call it a free-floating or rogue planet. Some of these objects may have formed like mini-stars, collapsing out of small clumps of gas in a turbulent nebula. Others could be planets born in disks around stars and later kicked out by gravitational scuffles. The label is less important than the physics. What matters is, they're small, they're cold, they're unbounded, they're hard to find. So how did Webb manage it? The team turned NIRISS, one of JWST's instruments, into a wide-field prism for an entire baby star cluster. Instead of taking a spectrum of one target at a time, they used slitless spectroscopy to disperse the light of every source in the field. That gives you a tiny rainbow for each object, enough to read molecular fingerprints that distinguish cool substellar bodies from background stars and galaxies. Spectra, not just brightness. That part is crucial. Brightness alone can fool you in a crowded nursery. Spectra give you chemistry and temperature clues that are harder to fake. NGC 1333, the target of this survey, is a compact star-forming region in the Perseus molecular cloud, roughly 1,000 light-years away. It's a messy neighborhood in the best possible sense: newborn stars, dusty filaments, jets, shocks. Environments like this are perfect for answering a hard question: how low in mass can the universe go when it forms objects the star-like way? If gas clouds fragment into pieces that act like tiny stars, where does that process stop? The Webb team retyped 19 known brown dwarfs, objects heavier than planets but lighter than stars. Don found 6 new candidates with L-type spectra consistent with planetary masses. Their estimated masses land between about 5 and 15 Jupiters, and one of them, down near 5 Jupiters, shows an infrared excess glow from warm dust consistent with a little circumplanetary disk. That disk is the eyebrower, sir. Think of a disk like a supply chain. Around stars, protoplanetary disks feed growing planets. Around giant planets, circumplanetary disks can feed moons. If a free-floating body at roughly 5 Jupiter masses is wearing a dust disk, it tells you 2 things. First, even very low-mass, unbound objects can host and process dust. Disk physics doesn't require a central star. Second, that disk had to form somehow. Either the object formed like a miniature brown dwarf with leftover material, or it was born in a stellar system and got ejected while still carrying its own mini-disk. Both paths are fascinating. One points to the universality of fragmentation in turbulent clouds. The other points to the chaos of young planetary systems ejecting worlds fast enough that they keep their accessories. Let's talk about the mass floor the survey hints at. Despite going deeper than previous searches, the team didn't find any objects later than mid-L-type, roughly speaking. Colder than you'd expect for masses below about 4 Jupiters at the cluster's age. That absence may mean Webb has reached the formation floor. In this particular nursery, cloud fragmentation seems to stall around for Jupiter masses. Below that, you might need a different mechanism, like a planet forming in a disk and then getting thrown out to populate the lowest masses. A floor isn't a hard law of nature, can shift with environment, metallicity, turbulence, magnetic fields. But finding a floor at all is a big clue. It tells you star-like formation doesn't run forever down into arbitrarily small clumps. Now the demographics. In this survey, when you combine the retyped brown dwarfs with the 6 newcomers, you get a striking fraction of free-floating planetary mass objects relative to the cluster. S members on the order of 10% in this sample. That's not a global constant. Each region can differ. But any double-digit percentage means these objects aren't rare curiosities in young clusters. They might be a standard product line, neither because turbulent clouds naturally fragment into planetary masses often, or because newborn planetary systems are rowdy enough to eject little worlds at a healthy rate. I want to dig under the hood for a moment and explain how spectra deliver masses. We don't weigh these objects on a scale. We compare their spectral types, how their molecular bands shape the Rainbow 2 models that tie temperature and luminosity to mass. Given an age. That given an age is the fragile piece. If the cluster is a little older or a little younger than you think, your mass estimates shift. That's why follow-up is essential. Confirming membership with proper motions, refining ages with multiple methods, and collecting more spectra to improve model fits. The team is transparent about this. These are the best estimates with the data in hand. And the point is not precision to the 10th of a Jupiter to its the population, distribution, and the edges of that distribution. Let's zoom back out. Why should you care about a handful of starless mini-worlds? Because they're boundary markers. They tell us where different formation channels start and stop. They help us map the seam between born like a star and born like a planet. And the tiny disk around the lightest candidate stretches our sense of what kinds of systems nature can assemble without a central sun. If moons can form around a free-floating 5 Jupiter mass object, that's a new category of miniature systems roaming the galaxy in the dark. There's also a practical upside to studying rogues. Without a host star glaring in the background, you can probe their atmospheres directly. Spectroscopy of isolated planetary mass objects has already revealed clouds, chemistry, and even aurora-like features in some nearby cases. Those measurements are hard to make on faint little worlds next to bright suns. Rogue is a storytelling word. Scientifically, these are laboratories for low-gravity atmospheres, worlds where we can test cloud models, dust formation, and weather without the complications of a dayside star beating down on them. Now, since this show leans date over hype, let's lay out the caveats plainly. First, cluster membership. In a crowded field, some background galaxies and reddened stars can masquerade as cool dwarfs. Spectra help, but proper motions and parallax over time seal the case. Second, mass model dependence. For very young ages, evolutionary tracks can diverge. The community keeps improving them with new benchmarks, but they aren't perfect. Third, the disk claim. The infrared excess is a solid sign of dust, but dust geometry, grain size, and background emission can complicate that signal. Additional JWST observations at multiple wavelengths and higher spectral resolution will sharpen the picture of that tiny disk hit's temperature, its mass, and whether it shows features like silicate bumps that shout real grains here. What could falsify or modify the story? Suppose deeper observations in an older or more quiescent cluster do find a significant population below for Jupiter masses. That would argue the floor moves with environment tanned that NGC 1333's turbulence or initial conditions set a local limit. Suppose proper motion follow-up shows 1 or 2 candidates aren't actually members. Then the fraction shifts, but the detection of multiple free-floating planetary mass objects remains. And suppose the disk candidate turns out to be a background object cleverly lined up. That would be disappointing for the lightest with a disk. Banner, but would leave the formation floor and rogue counts intact. That is the benefit of a population result. It is resilient to the fate of any single object. Let us connect this to the larger arc of planetary life and death we've been exploring in recent episodes. At one end, you have worlds that never had a sun. At the other, you have planets that lose theirs not because the star disappears, but because the star changes and the orbits decay. We've timed at least one hot Jupiter, WASP-1 to be. In a slow death, spiral its orbital period, shrinking by a few dozen milliseconds per year, evidence for tides dissipating orbital energy inside the star and the planet. We've even watched a sun-like star flare and dust itself as it swallowed a Jupiter-sized planet, with follow-up indicating the planet's orbit shrank over time before the final plunge, and long after the red giant fireworks fade. White dwarfs show metal pollution in their atmosphere's iron, calcium, magnesium that shouldn't be there unless they reactively accreting rocky or icy debris from disrupted minor planets. Put that together and you get a life cycle view. Some worlds never orbit. Some are born in orbits and later ejected. Some hang on too close and get erased. Some survive far out and send their fragments inward billions of years later. Why bring that up in a Rogue Planet episode? Because it changes how we count planets in the galaxy. If young clusters can produce or quickly eject planetary mass bodies at the 10% level, and aging stars can unmake inner systems and scatter leftovers for eons, the census of worlds is more dynamic than the word planet suggests. Today's bound exoplanet is tomorrow's rogue. Today's quiet debris belt is tomorrow's white dwarf pollution signature. The Webb result in NGC 1333 gives us a sharper look at the front end of that conveyor belt. The supply of unbound, low-mass objects right where stars are being born. Let's spend a few minutes on how to sanity check a claim like this when you see it in the news. First, ask Spectra or images. If a discovery hangs purely on "we saw a faint dot," be cautious. If it's S, "we saw a faint dot," and here S, it's spectrum with molecules that match a cool dwarf, that's stronger. Second, ask, what's the assumed age? Estimates at young ages depend on age. Third, ask, what's the floor? If the survey goes deep and still finds few or no objects below a certain mass, that tells you something physical. Finally, look for a plan for follow-up, proper motions, repeat spectra, and, where possible, longer wavelength data that can weigh disks and dust. Since many of you like numbers, here's the quick checklist from this study in plain language. 6 new free-floating planetary mass candidates with spectral types in the L-dwarf range. Estimated masses around 5 to 15 Jupiters, anchored by models appropriate to a very young cluster. 1 object near 5 Jupiters showing an infrared excess consistent with a circumplanetary dust. Disk potentially the lightest object known with a disk. No detections of colder, later type objects that would correspond to masses below roughly 4 Jupiters at this age, and a resulting implication that free-floating objects could account for a surprisingly large slice of members in this cluster. What comes next? Proper motion confirmation to lock in membership. Deeper JWST spectroscopy to refine temperatures and gravities. Those are the knobs that tighten mass estimates. Mid-infrared observations to dissect the disk candidate's dust. Is it warm silicate grains? Is there evidence of grain growth? How much mass are we talking about? And parallel surveys of other clusters of different ages and environments to see whether the floor and the fraction of rogues change. If NGC 1333 is a hotspot for low-mass fragmentation, you should see fewer rogues in a less turbulent region. If ejection dominates, you may see the rogue fraction track the frequency of early giant planet instabilities. There's also an opportunity here to connect formation to weather. Once you have a clean sample of isolated planetary mass objects, you can chase time-variable features in their spectra, signs of patchy clouds rotating in and out of view, condensate species forming and evaporating, even hints of auroral processes if they carry magnetic fields and interact with surrounding plasma. Every rogue world you study this way becomes a bridge between exoplanet climate models and brown dwarf atmosphere models. In a regime where gravity is low and clouds behave differently, I'll close by addressing a quiet, worrisome people have when they hear rogue planets. Are these things dangerous, wandering through space like pool balls? Space is big. The chance of a free-floating 5 Jupiter mass object wandering close enough to our solar system to matter is extraordinarily small on human timescales. The right way to think about rogues is not as threats, but as messages. Natural experiments that let us see what low-mass, cold worlds are like without the glare of a star. And population markers that reveal how often the universe makes solar ejects worlds at the edge of planethood. So the headline hides a deeper story. Webb didn't just spot 6 lonely worlds, sketch the shape of a boundary. The lowest masses nature seems to reach when it forms objects the star-like way in this nursery. And the surprising prevalence of free-floating planetary mass bodies among newborn stars. It added a rare specimen, a featherweight, wearing a disk to remind us that even tiny objects can host miniature systems. And it plugged a new data point into the longer arc of planetary evolution. From worlds that never had a sun, to worlds that lose theirs, to the ashes of worlds recorded in the atmospheres of stellar remnants. If you like your astronomy with method first, how we measured, how we know, and what we still don't, this is one of those results that rewards careful reading. It's not a splashy single image. It's a map of a population, an edge, and a supply chain. And it sets up years of follow-up that will either reinforce the floor, shift it, or split it into environment-dependent floors across the galaxy. Any of those outcomes would teach us something important. Before we wrap, 2 takeaways you can carry with you. First, Spectra beats snapshots. When you're weighing claims about faint, cool objects in messy nurseries, molecular fingerprints are the gold standard. Second, edges matter. Knowing where a process stops like starlight formation around 4. Jupiter masses here tells you how nature partitions its work among different mechanisms. It's the difference between seeing a list of objects and seeing a theory take shape. That's our tour of Webb's rogue planet candidates in NGC 1333, what they are, how we found them. Why one of them's dusty little disk is such a big clue, and where the next questions point. Episodes like this help you separate data from drama. Subscribe and send me the next topic you want unpacked.